Next up, if we're going to introduce the inverse tangent function, we first need to consider the graph of the tangent function. Now, similar to what we saw for the sine and the cosine, the tangent function fails the horizontal line test due to the fact that any horizontal line that hits the graph, which would be any horizontal line, is going to intersect the tangent function once per period. Now, that would be an infinite number of times, as there are an infinite number of periods. So once again, we are going to restrict the domain. Now, same rules apply as before. I'm interested in angles that are close to x equals 0, and I'm interested in connecting a maximum to a minimum. However, for the tangent function, a minimum would be down to negative infinity, and a maximum would be up to positive infinity. So from here, I'm simply going to go down to where we see our first asymptote to the left of x equals 0, and up to where we see our first asymptote to the right of x equals 0. These asymptotes will occur at negative pi over 2 and positive pi over 2. So here is the domain restriction that we will be using. Y is equal to the tangent of x, and x will be between negative pi over 2 and positive pi over 2. This domain restriction is similar to what we saw for the sine function. The difference is that for the tangent function, we are not going to include the endpoints of the interval. The reason that we don't include the endpoints is those are asymptotes, and we can't be equal to things that are asymptotes. Now, on the unit circle, if we're talking about angles that are between negative pi over 2 and positive pi over 2, we would be talking about all of the angles that exist within quadrant 4 as well as quadrant 1, with the knowledge that quadrant 4 angles are simply going to be negative angles and quadrant 1 angles will be positive angles. This function is 1 to 1, and so that's the restriction that we are going to use. So we will define the inverse tangent function. The inverse tangent function is also known as the arctangent function. Saying that y equals the arctangent of x is equivalent to saying that the tangent of y is equal to x, with the following restrictions. Y is now referring to the angle. We just said that the angle has to be between negative pi over 2 and positive pi over 2. X is going to be the corresponding ratio. Now that would be the range of the original tangent function, which happens to be all real numbers. So we'll use this notation to let us know that x is an element of the set of all real numbers. Additionally, if we were to take a look at the graph of y equals the arctangent of x, this is a very unique graph for the following reason. It is one of very few graphs that is going to have two different horizontal asymptotes. These correspond to the two vertical asymptotes of the original tangent function, which is why one of your horizontal asymptotes is going to be y equals positive pi over 2, and the other one is going to be y equals negative pi over 2. This is something that shows up rather frequently in calculus, so please make note of it. Now, to evaluate arctangents, this becomes a little bit more complicated because we're not simply grabbing points from the unit circle. So for example, if I asked you to find the arctangent of 1, I am looking for the angle on the unit circle whose tangent is equal to 1. Now, rather than simply looking for ordered pairs, what I might consider having you do is set up an angle so that the opposite over the adjacent is equal to 1. Opposite over adjacent is equal to 1. Applying the Pythagorean theorem tells us that the hypotenuse would be the square root of 2, letting us know that we are looking for the angle associated with 1 over the square root of 2 and 1 over the square root of 2. That angle is going to be equal to pi over 4. This is due to the fact that, that's not how you spell because, bet. Because the tangent of pi over 4 is equal to 1, and pi over 4 is in the appropriate restriction. We could also evaluate something along the lines of the arctangent of -1 over the square root of 3. Setting this one up similarly to what we did for the last one, I'm looking for the angle. Because the ratio is negative, we'll be looking in quadrant 4. And I want the ratio of the opposite over the adjacent to be 1 over the square root of 3. So a 1 over here, and the square root of 3 over here, and we'll call this guy theta. However, because we're in quadrant 4, we will want the 1 to be negative. Applying the Pythagorean theorem lets us know that the hypotenuse is going to be 2. So really, the point that I'm looking for on the unit circle is the following point. The cosine would be root 3 over 2, and the sine would be -1/2. That, of course, corresponds to -pi over 6. This is due to the fact that the tangent of -pi over 6 is equal to the desired ratio, -1 over the square root of 3, and -pi over 6 is within the appropriate angle restriction of -pi over 2 to +pi over 2. Now, because the domain of the inverse tangent function is all real numbers, please know that there are, you could literally input anything to the inverse tangent function and you will get an answer. These just happen to be the most common ones that we talk about. So the inverse tangent of 1 over the square root of 3 happens from the 30-degree angle. The arctangent of 1 happens from the 45-degree angle, and a tangent of the square root of 3 happens from the 60-degree angle. Measured in radians, those would be pi over 6, pi over 4, and pi over 3. Commit these to memory.